All right. Excuse my hood. It's really cold today, and I'm cold, so I'm going to just stay warm. All right. So we left off here. So I think somewhere in the middle of the page, but I'm going to start over here because my memory is fuzzy. Here we go. Instead, we need a loss function that, when our weights result in slightly better predictions, gives us slightly better loss. So what does a slightly better prediction look like exactly? Well, in this case, it means that if the correct answer is a 3, the score is a little higher. Or if the correct answer is a 7, the score is a little lower. So let's write such a function now. What form does it take? The loss function receives not the images themselves, but the predictions from the model. So let's make one argument PRDS of values between 0 and 1, where each value is the prediction that an image is a 3. It is a vector, rank 1 tensor, so a 1D array indexed over the image. Okay, so I think we did something like this on the previous one. The purpose of the loss function is to measure the difference between predicted values and the true values. The difference, that is, the targets labels. Therefore, make another argument targets with values of 0 or 1. So that's the ground truth that tells us whether an image is actually a 3 or not. It is also a vector, another rank 1 tensor indexed over the image. So PRDS is the predictions of the model for each value, each I guess corresponding element is for that image, whether or not it is a 3. So ideally, if a prediction is really low, like close to 0, then it knows that that's actually more of a 7. Okay, I'm just kind of regurgitating everything. So for instance, suppose we had 3 images that we knew were a 3, a 7, and a 3. And suppose our model predicted with high confidence 0.9 that the first was a 3, with slight confidence 0.4 that the second was a 7, and a fair confidence 0.2, but incorrectly that the last was a 7. So 0.2 means that it can't be a 3, even though the ground truth says it is a 3. So when it's low like this, it's assuming it's a 7 with fair confidence. This would mean that a loss function would receive these values as inputs. So loss function receives these things. And here's a first try at a loss function that measures the distance between predictions and targets. So there's this mness loss. You're given one tensor, 1D tensor of predictions, and a 1D tensor of targets. So two arrays. What you want to do is you want to find all the targets where it is a 3. Then you want to just subtract 1 from every element in predictions. So this will be like 0.1, 0.6, and then this will be 0.7, and then the prediction itself. So I don't know what these arguments actually mean for where, but I'm just kind of just doing the math. So targets here would be like true, false, true, and then 1 minus predictions would be just what I just said, and then predictions itself would just raw right here, and then we'll take the mean. Okay, so we're using a new function, torch.where ABC. This is the same as running the list comprehension B. So you're taking B, so you're taking this. If this is true, the element here is true, else use this one for every single element in the matrix of this one, okay, or tensor of this one, except it works on tensors. Okay, so we're basically building a new tensor here that It's going to take an element from either this or this based off of this. So if it's true, you want to pick this one, the inverse. If it's false, you want to pick this one here. But why? How does that reflect the loss? Especially when you use dot mean. So in plain English, this function will measure how distant each prediction is from 1 if it should be 1, and how distant it is from 0 if it should be 0, and then take the mean of all those distances. Okay. I see. So given like the specific ground truth, right? Given the specific ground truth, how far are you away from that ground truth given that prediction? So let's say if you were supposed to be a 3, well, how far are you away from it based off of your prediction? How off were you? So this one's 0.1 off. Okay, that sort of makes sense now. Okay. Then the mean of that, so it's just like on average, what was your distance? So read the docs. It's important to learn about PyTorch functions like this. I should, because looping over tensors in Python performs at Python speed, not C or CUDA speed. Try running help torch.where now to read the docs for this function, or better still, look it up on the PyTorch documentation site. So let's try it on our PRDS and targets. So predictions and targets. So now when we do this, we're going to get this. So we just solved that. Well, not really. We solved this, but I guess we need to just do this exercise in picking out the answer. So in this case here, if it's a 1, we pick 1 minus this, which is going to be 0.1. This will be a 0, so that's just going to be 0.4. So 0.1, 0.4. And then this one will be 1 minus 0.2. I said 0.7 before, huh? No, it should have been 0.8. 0.8. So 0.1, 0.4, 0.8. Cool. So you can see that this function returns a lower number when predictions are more accurate. When accurate predictions are more confident, okay? So basically your distance is smaller from the ground truth, that's actually more accurate. Okay, so when accurate predictions are more confident, higher absolute values, and when inaccurate predictions are less confident, in PyTorch, we always assume that a lower value of a loss function is better. Since we need to find a scalar for the final loss, this loss takes the mean of the previous tensor. Okay, so this 0.4333. For instance, if we change our prediction for the one false target from 0.2 to 0.8, the loss will go down, indicating that this is a better prediction. One problem with MNIST loss, as currently defined, is that it assumes that predictions are always between 0 and 1. We need to ensure that then this is actually the case. As it happens, there is a function that does exactly that. Let's take a look. Okay, sigmoid. That will just make sure that predictions are always between 0 and 1. So the sigmoid function always outputs a number between 0 and 1. It's defined as follows. Def sigmoid return 1 over 1 plus pretty much e to the negative x. PyTorch defines an accelerated version for us, so we don't really need our own. This is an important function in deep learning, since we often want to ensure that values are between 0 and 1. This is what it looks like. So here's what a sigmoid function looks like. So the y values are always between 0 and 1, given any sort of x. So if we have a very, very small x, it will just be very, very close to 0. Very, very high x's, it will flatten out, getting close to 1. So as you can see, it takes any input value, positive or negative, and smooshes it into an output value between 0 and 1. It's also a smooth curve that only goes up, which makes it easier for SGD to find meaningful gradients. So let's update MNIST loss to first apply sigmoid to the inputs. So predictions.sigmoid, and then we do this MNIST loss. So I think let's actually code that now. Let's define that MNIST loss function. Just kind of get rid of this. Okay. You know, I think it's time to actually just reduce this font size. I've been watching some of these videos, and I think it's plenty big enough as it is. It just gets in my way sometimes. Okay, let's reduce that to 16, and then terminal. Oops, wow, that was weird. Terminal font size. Yeah, see, my hands are so cold that I can barely hit the space bar. Okay, there we go. Okay, so now we have a much smaller font size, but what that allows us to have is more screen real estate. Okay, def mnist loss predictions targets. Predictions is going to be predictions.sigmoid, and then return torch. Maybe something's just stuck in my space bar. It's a cheap laptop. Okay, torch.where. Sorry for all the key slamming. Targets is 1 minus predictions, and then predictions themselves. Okay. So, function defined. Okay, so now we can be confident our loss function will work even if the predictions are not between 0 and 1. All that is required is that a higher prediction corresponds to a higher confidence. Having defined a loss function, now it is a good moment to recapitulate why we did this. After all, we already had a metric, which was overall accuracy. So why did we define a loss? The key difference is that the metric is to drive human understanding and the loss is to drive automated learning. To drive automated learning, the loss must be a function that has a meaningful derivative. It can't have big flat sections and large jumps, but instead must be reasonably smooth. This is why we designed a loss function that would respond to small changes in the confidence level. This requirement means that sometimes it does not really reflect exactly what we are trying to achieve, but is rather a compromise between our real goal and a function that can be optimized using its gradient. The loss function is calculated for each item in our data set, and then at the end of the epoch, the loss values are all averaged and the overall mean is reported for the epoch. Metrics, on the other hand, are the numbers that we care about. These are the values that are printed at the end of each epoch and tell us how our model is doing. It is important that we learn to focus on these metrics rather than the loss when judging the performance of a model. SGD and mini batches. Now that we have a loss function suitable for driving SGD, we can consider some of the details involved in the next phase of the learning process, which is to change or update the weights based on the gradients. This is called an optimization step. Okay? So to take an optimization step, we need to calculate the loss over one or more data items. How many should we use? We could calculate it for the whole data set and take the average, or we could calculate it for a single data item. But neither of these is ideal. Calculating it for the whole data set would take a long time, and calculating it for a single item would not use much information. So it will result in an imprecise and unstable gradient. Okay, you'd be going to the trouble of updating the weights, but taking them into account only how it would improve the model's performance if that was like a single item. So instead we compromise. We calculate the average loss for a few data items at a time. This is called a mini batch. The number of data items in the mini batch is called the batch size. A larger batch size means that you will get a more accurate and stable estimate of your dataset's gradients from the loss function, but it will take longer and you will process fewer mini batches per epoch. Choosing a good batch size is one of the decisions you need to make as a deep learning practitioner to train your model quickly and accurately. We will talk about how to make this choice throughout this book. Another good reason for using mini batches rather than calculating the gradient on individual data items is that in practice, we nearly always do our training on an accelerator such as a GPU. These accelerators perform well only if they have lots of work to do at a time. So it's helpful if we give them lots of data items to work on. Using mini batches is one of the best ways to do this. However, if you give them too much data to work on at once, they run out of memory, making GPUs happy is also tricky. Cool. As you saw in our discussion of data augmentation in chapter 2, we get a better generalization if we can vary things during training. One simple and effective thing we can vary is what data items we put in each mini batch, rather than simply enumerating our data set in order for every epoch. Instead, what we normally do is randomly shuffle it on every epoch before we create the mini batches. PyTorch and fastai provide a class that will do the shuffling and mini batch collation for you called data loader. Okay, so that answers the question, right? Like, if you were to perform multiple epochs and you take mini batches, these items will be reshuffled anyway on the next epoch, so then you never have, or the chances of you having a mini batch on one epoch and the same one on the next epoch are pretty low. A data loader can take any Python collection and turn it into an iterator over many batches like so. Okay. For training a model, we don't just want any Python collection, but a collection containing independent and dependent variables, the inputs and the targets of the model. Okay, a collection that contains tuples of independent and dependent variables is known in PyTorch as a data set. Here's an example of an extremely simple data set. So a data set, an object that is of data set class. So we're going to enumerate through all the lowercase ASCII characters. And then we're going to turn that to a list, I assume. This is like a fastai thing. So then now you have a tuple of the ASCII string lowercase when turned to a list. Okay, so enumerate will always like give you back the item and then like the index and then yeah. Okay, when we pass a data set to a data loader, we will get back many batches that are themselves tuples of tensors representing batches of independent and dependent variables. Okay, batch size 6 is just basically 6 items. Is that true? 1, 2, 3, 4, 5, 6. Yep. 1, 2, 3, 4, 5, 6. Okay, so it'll be like 17R, 18S, 10K, and so on. Okay. So now we are ready to write our first training loop for a model using SGG. So putting it all together, it's time to implement the process we saw in figure 4-1. In code, our process will be implemented like this for each epoch. So for x, y, and DL, pred equals model x, so that's doing a forward pass to predict. Loss equals loss func, so that's going to be the mnist loss. In this case, predictions and targets. Targets will be y. Then we do backwards, which is going to apply whatever to, in this case, like the model's weights, the parameters, right? And then you basically update them by multiplying the gradient with the learning rate. So higher learning rate is going to be a bigger adjustment here. So let's do that. But we need to create a data loader, right? Oh, I think it's going to walk us through. Okay, so first let's reinitialize our parameters. Okay, let's reinitialize our parameters. So weights init params 28 times 28 1. Okay, let's also get rid of this. What else do we have? We have bias. We want to init those params too. And then we want to create a data loader. So DL equals data loader. Dset. batch size 256. Did we even create a data set? I guess we did. I don't even remember. So xb, yb, so that's going to be the first item, I'm assuming. xb.shape, yb.shape. Batch size, oh, should be an underscore. Okay, cool. 256, 784, 256, 1. So these are 256 labels, elements. And then these are 256 images where it's like flattened out the pixels. Okay. So batch size is 256. Then the validation set is the same. Valid DLs, data loader, valid dset. And then batch size is going to be 256. Oops. Okay, so batch. Mini batch size 4, so train X is going to be, wait, did we even create train X? No. So how's that going to work? Oh yeah, we did. We had it from the other. Okay, so create this, batch.shape. Okay, so we have 4. We're going to do predictions. So we did the linear 1. We're going to call the linear 1 function that we wrote on the batch and output preds. Okay. Again, we're a different random like seed, so numbers are going to be different. Now we're going to calculate the loss off the predictions and this loss. Did we update that? Yes, we did. Okay. So now that's going to be preds. And we also have some targets. So we're just going to take the first, 4 items from train Y. And then we also want to output the loss. Okay. Did I not do dot mean? Let's see here. Oh yeah, I didn't do dot mean. Okay, dot mean. Okay, redefine that. Run that again. Tensor 1. Why is that? Tensor 1. Targets equals 1. 1 predictions. Predictions.sigmoid. Yes. Isn't that correct? One minus predictions and mean. Yes. I feel so silly. I don't know. Oh, it's this dimension thing again. Right here. Okay. Why did I not? I think I know why. Okay, so it all goes back to here, I think. Yeah. So my 28, 1 thing, I did the same mistake again. Okay. Right there. Okay, so that's where I went wrong again. Surprise, surprise. And now it should look better. Okay. Still kind of weird, but at least it's something, right? It's a low loss. But that's okay. I mean, the data shape is fine now, and I think it's just like random, like again, random numbers, right? So if I can just init, I just got a different init. So yeah, I'm just getting different inits, that's all. So getting just different generation of weights. So it's not going to be exactly like his, but this one seems pretty close. Okay, so now we calculate the gradients. Okay, loss backwards, or loss dot backward, and then weights dot grad dot shape. and then weights.grad.mean, then bias.grad. Okay, so what do we have here? We have 784, I guess, gradients, and then the mean is going to be we're going to change the weight by negative 0.0144, and the bias for negative 0.0910. Okay, then we can just put that all into a function. Calc grad. We're going to do the prediction. So we're going to do the forward pass. Then we're going to just take that result of the forward pass, compare it, or just calculate the loss against the ground truth. Then we're going to do loss that backwards. Okay. Def calc grad xb yb model preds is going to be the forward pass in the model. Then we're going to calculate the loss with preds yb. So yeah, preds is off from this forward pass. And then we're going to just loss dot backward. So handy helper function. Okay, so how does that relate with our so with our current results, we didn't adjust anything yet, so we can just reuse things. So take our batch, our mini batch of 4 elements, and then take this here, and then linear 1 will be our forward pass function, and then we can just output things again, and it should be relatively the same. Or is it? No. Interesting. Did we adjust? Oh, did the backward really did adjust stuff? No, it shouldn't have. Right? Shouldn't have. Okay. Well, I guess it did for him too. The gradients have changed. Oh, okay. Yeah. So the gradients have changed. I didn't expect that. The reason that for this is that loss.backward adds the gradients of loss to any gradients that are currently stored. So we have to set the current gradient to 0 first. Okay. Yes, I had not expected this to change. That's the reason why. So I'm assuming we could do that in front. We can do this to reset before calcgrad, or should we do it before we call calcgrad? But I'm guessing this is the part of the training loop. That's the whole point, right? I'm guessing so. So let's do that. Weights dot. No, I don't feel like that's correct. I think we should just do it here. Yeah, I really don't feel like that's the right thing to do. Weights dot grad dot zero them out. Bias dot grad dot zero them out. And then we will always get the same thing over and over again. Okay, cool. Okay, so we removed stored gradients on the weights and the biases. Okay, in place operations. Methods in PyTorch whose names end in an underscore, always wondered, modify their objects in place. For instance, bias.0_ sets all elements of the tensor bias to 0. Our only remaining step is to update the weights and biases based on the gradient and learning rate. Okay, so that's when we actually apply the changes into the weights and biases. When we do so, we have to tell PyTorch not to take the gradient of this step too. Otherwise, things will get confusing when we try to compute the derivative at the next batch. If we assign to the data attribute of a tensor, PyTorch will not take the gradient of that step. Here's our basic training loop for an epoch. Okay, so for every single example in your data loader, you want to calculate the gradient. Then you want to update with .data for every single parameters. Okay, so what's that going to be passed in as? Is that just the weights and the bias, or if we assign it to the data attribute? Okay, so let's read this again. So our only remaining step is to update the weights and biases based on the gradient and learning rate. When we do so, we have to tell PyTorch not to take the gradient of this step 2. Not to take the gradient of this step 2. Huh. Otherwise, things will get confusing when we try to compute the derivative at the next batch. If we assign... Oh! Zeroed them out? If we assign the data attribute of a tensor, PyTorch will not take the gradient of that step. Here's our basic training loop. Oh, so we had to assign the data attribute. We had to do it this way. Otherwise, PyTorch is going to take the gradient of that step and we're just going to zero it out. Okay. Makes kind of more sense. Okay. So let's write that function. Okay. So def train epic model LR params for xb yb in DL. We want to calc grad on xb yb model, and then for every parameter in params, what we want to do is we want to modify it by using the gradient times the learning rate, and then we want to zero out the gradient. Okay, done. So we also want to check how we're doing by looking at the accuracy of the validation set. To decide if an output represents a 3 or a 7, we can just check whether it's greater than 0. So our accuracy for each item can be calculated using broadcasting as follows. So this can just be the accuracy, okay? So that gives us this function to calculate our validation accuracy. So batch accuracy is going to be, first of all, perform the sigmoid function. Then if we're over 0.5, if our prediction is over 0.5, it means that we are going to be a 3. Okay, that's quite generous, but sure. Batch accuracy, xb yb, preds, xb.sigmoid. And then correct is going to be take your predictions, check every single element if it's above 0.5. And if it is, that's a true. We're going to match it up with every single true false inside YB. Return correct.float.mean. Okay. Now we can check it works. Sure. Batch accuracy, linear 1, batch, train Y. Take the first 4 examples. And what do we get? A tensor mean. Function tensor mean. Oops. There we go. 0.75. Okay, so we're 75% accurate. And then put the batches together. Ooh, okay, validate epic. Okay, so def validate epic model. I don't know what ACCS is. Accuracies, a bunch of accuracies. So all the batches. So model xb yb for xb yb invalid DL. So all the take all the batches, take all the accuracies, and then return round torch.stack all the accuracies, put them all together, take the mean. Then there should be one item in there, and then what's for this one? 4-digit precision. Okay, then we have validate epic linear 1 is going to be our forward pass function. Ack is not defined. Ax. There we go. So 0.6241 is our initial accuracy across our batches. Okay, so that's our starting point. Let's train for 1 epic and see if the accuracy improves. Okay, LR is going to be 1 dot, so 1 e to the 1 e to the, was it 1 in this case? No, when each is 0, sorry. Params equals weights bias train epoch. It's going to be the forward pass function, learning rate, all parameters, validate the epoch, linear 1 again, and missed that, typing too fast. So after one pass, 0.8583. Cool. So let's do 20 epochs. It says to do 20 epochs. Okay, for I in range 20, train epoch, linear 1, LR, params, print, validate epoch, linear 1, end. All right. Cool. We got to be pretty accurate at the end, 0.75. Maybe I should have added a space like he did. Okay, there we go. Okay, 0.98 because I trained one more time, another 20 epochs. Anyway, looking good. We're already about the same accuracy as our pixel similarity approach, and we've created, let me just shrink this slightly. Yeah, okay, we've already created a general purpose foundation we can build on. Our next step will be to create an object that will handle the SGD step for us. In PyTorch, it's called an optimizer. Creating an optimizer. Because this is such a general foundation, PyTorch provides some useful classes to make it easier to implement. The first thing we can do is replace our linear function with PyTorch's nn.linear module. A module is an object of a class that inherits from the PyTorch's nn.module class. Okay, so nn.linear is a child class of nn.module. Objects of this class behave identically to standard Python functions in that you can call them using parentheses, and they will return the activations of a model. Activations are the results. nn.linear does the same thing as our init params and linear together. It contains both the weights and biases in a single class. Here's how we replicate our model from the previous section. So we can create a new model that's just linear, a linear model using nn.linear with this many parameters. Okay, so in features, it's going to be 784 parameters. Out features, how many are coming out? Only one thing, one answer. So every PyTorch module knows what parameters it has that can be trained. They are available through the parameters method. So weights and biases, linear model.parameters. Okay, so let's do that. WB equals linear model dot parameters, and W shape, B shape. Cool. So 784 parameters for the weights, and then 1 for the bias. Okay, so we got exactly that. So we can use this information to create an optimizer. So we're going to have a basic class, and zero grad is going to also just zero out the gradients of the specific parameters. Self.params, self.lr equals list params. So params is going to have both list params, so turn the parameters into a regular Python list, and then you have a learning rate that gets assigned here to self.lr. Step is going to do what we did, I think, where was it? Up here. Yep, so that's what it does. Okay, and then zero grads is 0. Okay, cool. So let's just implement that. Class basic. Man, my spacebar is like stuck. Basic optim, and this laptop's only a few months old. Basic optim def init self params lr, self dot params equals list params, and then we have self dot lr equals lr. Okay, and then we'll define step self args keyword args, so it's like a spread for p in self dot params. What do we want to do? P dot data minus equals p dot grad dot data times self dot lr. So we adjust p dot data by the gradient of that parameter times the learning rate. Okay, and then we're going to zero. We have a method to zero out gradients for the parameters list. So zero grad self args keyword args for p in self dot params pin p in self dot params. What do we want to do? P dot grad equals none. Okay, so just like to explain, let's see. Okay, so here we go. If anybody's wondering, difference between arguments star args and star keyword args in a Python method signature. Okay, so in a Python method signature, star args positional args is going to be basically the extra positional arguments in a tuple. Okay, so let's say that we have a function here and we have a mandatory argument a and then a bunch of other arguments defined as star args. Now star args is going to be passed in as a tuple. So in this case here, a is passed in, or 1 is passed in as a, and then a this 2, 3, 4 will get converted to a tuple. Now keyword args is going to be passed in as dictionary, right? So you'll have one mandatory one, and you'll have like the rest here. Okay, so this will be 1, and then this will be x and y. So this gets passed in. X and y gets passed in as a dictionary in this case. Okay, and the keys here of the dictionary corresponds to the variable names you pass them in as. Now this is using both here is just going to be the first parts are going to be tuple, and then keyword args you're going to name those arguments with keys and values. Now caveats here is that star args must always come before the keyword arguments. Keyword arguments in practice is always going to be the last one. Okay, so now the question is, why would we want to define a function that takes mandatory star args and star keyword args all at the same time? Okay, because it lets you write a function that requires a minimal contract, accepts extra stuff without breaking, and can pass through unknown arguments to something else. So they're good as like wrapper functions. So passing through, right? So we can write a wrapper function that, okay, maybe give a function, you give the arguments, and you give the keyword args. So mandatory params can capture what you need, while star args and star keyword args for the rest. Okay. But the question is, let me just try to find it. Why include no? Because that's a clear minimum. But I am wondering, why would we use star args to begin with if we can use keyword args? Okay, so yeah, args is for extra positional arguments ordered and unnamed, right? So let's say your max function has like mandatory 3 arguments. We can pass in the first argument as mandatory, and we can pass in like the tuple as like the rest in this case. So that's when like order matters. Okay, order matters here. It's like passing in the rest of the arguments in any other function. Okay, I think that's enough. We can just keep going. Just wanted to call that out. Where's my Firefox? Did my Firefox crash? Oh, don't tell me it did. Oh no, it's right here. Well, that's odd. Why do... Okay, I'll just pretend. Okay, anyway. Okay. So we can create our optimizer by passing in the model's parameters. So let's create an optimizer. Opt basic optim linear model dot parameters, and then with a learning rate. So I didn't run this yet. Right here, there we go. It's hard to program in a notebook. It's hard to see, especially screen real estate is like so small. Okay, and then now training loop is even easier. So def redefine train epic with model passed in for xb yb in data loader. We're going to calculate the gradient xb yb model. We're going to opt.step and then opt.0grad. Okay, and then validate epic linear model. Okay, so 0.5, because we initialize a random set of weights, right? So now it's time to just train. So def train model, we're going to call train epic inside here. So how many epics you want inside. So for I in range epics, so how many epics? We're going to go through each epic and we're going to train. I'm going to call train epic on that model. So okay, train epic on that model, and then we're going to print validate epic model n, so just a separator. Okay, there we go. So now we have this function defined, and we're going to just train our model for 20 epics. So right now our loss is 0.5, or accuracy is 0.5, and after 20 we expect it to be 97 or so. So 20 epics, 97 or so. Let's do it. Okay, what do we end up with? Yeah, about 97. So it looks like it maxes out for him at 97.85. For us, it's also 97.85% accuracy. Okay, so fastai provides the SGD class that by default does the same thing as our basic optim. So that's also provided. So let's create a new linear model again. So we're going to reset everything. Create n.linear 28 by 28. One output opt SGD linear model dot parameters with a learning rate passed through, and then train model linear model 20. So again, train model is going to just I guess like implicitly use opt, which we had redefined down here. I would argue that maybe you should pass in opt, but that's okay. So fastai also provides learner.fit, which we can use instead of train model. To create a learner, we first need to create a data loaders by passing in our training and validation data loaders. Okay, so create a proper data loaders. Was it DL? Valid DL. Okay, so we created a proper data loaders. To create a learner without using an application such as CNN Learner, we need to pass in all the elements we've created in this chapter. the data loaders, the model, and the optimization function, which will be passed the parameters, the loss function, and optionally any metrics to print. So let's do that. Let's create our own learner. So that'll just like when we call learner.fit, it'll use all that information to just fine tune or train. So learn is learner. What do we need? We need data loaders. We need weights pretty much. So the model. Oops. Okay, we also need the optimization function, which is going to be SGD. We also need the loss function. That's going to be the mnist loss. And then the metrics function, so batch accuracy. Or is it batch accuracy? There we go. Okay, so we have all that good to go. Let's just make that look better. There we go. And then here. Okay. All right. And then there we go. So call learner.fit. Let's learn.fit. 10 epochs. Learning rate is going to be whatever learning rate we had to find, which is like 1, I believe. So let's do that, and boom, all good. Accuracy 0.967. Cool. So yeah, all this is equivalent to everything we've just done in the previous cells. So as you can see, there's nothing magic about the PyTorch and fastai classes. They are just convenient prepackaged pieces that make your life a bit easier. They also provide a lot of extra functionality we'll be using in future chapters. With these classes, we can now replace our linear model with a neural network, adding a non-linearity. So far, we have a general procedure for optimizing the parameters of a function, and we have tried it out on a boring function, a simple linear classifier. A linear classifier is constrained in terms of what it can do. To make it a bit more complex and able to handle more tasks, we need to add something nonlinear, basically something different from ax plus b, between the two linear classifiers. This is what gives us a neural network. So here is the entire definition of a basic neural network. It's just basically what your parameters or your input, matrix multiplied by your weights of the model, plus some sort of bias. Then what do we do? The result, so we're going to take the max. I don't know what tensor 0.0 is. And then we're just going to multiply it by another set of weights, plus another bias, and we return the result. Okay? I think this is probably just like an activation function. This is supposed to represent one. Okay, so that's it. All we have in SimpleNet is two linear classifiers with a max function between them. Here, W1 and W2 are weight tensors, and B1 and B2 are bias tensors. That is, parameters that are initially randomly initialized, just as we did in the previous section. So we initialize 784 and 30 outputs. Bias is just going to be 30 to correspond to that. W2 is going to be taking in 30, reducing it to 1. Same thing with B2. It's just going to be 1 in this case. So yeah, so bias corresponds to every single out feature. So the key point is that W1 has 30 output activations, which means that W2 must have 30 input activations, so they match. That means that the first layer can construct 30 different features, each representing a different mix of pixels. You can change that 30 to anything you like to make the model more or less complex. That little function res.max tensor 0.0 is called a rectified linear unit, also known as ReLU. Oh, that's what it was. Okay. We think we can all agree that rectified linear unit sounds pretty fancy and complicated. But actually, there's nothing more to it than a result.max tensor.0.0. In other words, replace every negative number with a 0. Okay. This tiny function is also available in PyTorch as f.relu. Okay. Plot function f.relu. Do we have a plot function here? Yes, we do. f.relu. Okay, cool. Jeremy says, there is an enormous amount of jargon in deep learning, including terms like rectified linear unit. The vast majority of this jargon is no more complicated than it can be implemented in a short line of code, as we saw in this example. The reality is that for academics to get their papers published, they need to make them sound as impressive and sophisticated as possible. One way that they do that is to introduce jargon. Unfortunately, this results in the field becoming far more intimidating and difficult to get into than it should be. You do not have to learn the jargon, because otherwise papers and tutorials are not going to mean much to you. Oh wait, you do have to learn jargon, because otherwise papers and tutorials are not going to mean much to you. But that doesn't mean you have to find the jargon intimidating. Just remember, when you come across a word or phrase that you haven't seen before, it will almost certainly turn out to be referring to a very simple concept. So with this activation function here, what it's doing is that it's just replacing every single element that is not or the y part. If it's less than 0, it's just going to become 0. That's why it's straight here. Otherwise, if it wasn't a ReLU and let's say it was linear, it would just be a straight line down like this, right? But then since now the ReLU will take everything that is negative on the y-axis and just turn it into 0, it becomes a straight line, and then we just shoot straight up. Okay. So the basic idea is that, and all these y's right here, these outputs will be fed into the second layer. So that one is where you multiply with W2. Okay, so the basic idea is that by using more linear layers, we can have our model do more computation and therefore model more complex functions. But there's no point in just putting one linear layout directly after another one, because when we multiply things together and then add them up multiple times, that could be replaced by multiplying different things together and adding them up just once. So there's no point. That is to say, a series of any number of linear layers in a row can be replaced with just a single linear layer with a different set of parameters. But if we put a nonlinear function between them, such as max, this is no longer true. Now each linear layer is somewhat decoupled from the other ones and can do its own useful work. The max function is particularly interesting because it operates as a simple if statement. Sylvain says, mathematically, we say the composition of two linear functions is another linear function. So we can stack as many linear classifiers as we want on top of each other. And without nonlinear functions between them, it will just be the same as one linear classifier. Amazingly enough, it can be mathematically proven that this little function can solve any computable problem to an arbitrarily high level of accuracy if you can find the right parameters for W1 and W2. And if you make these matrices big enough, for any arbitrarily wiggle function, we can approximate it as a bunch of lines joined together. To make it closer to the wiggly function, we just have to use shorter lines. This is known as the universal approximation theorem. The 3 lines of code that we have here are known as layers. The first and third are known as linear layers, and the second line of code is known variously as a nonlinearity or activation function. Okay, so this is an activation function, so I'm guessing we just convert one thing to another. So just as in the previous section, we can replace this code with something a bit simpler by taking advantage of PyTorch. So simple neural net is going to be a sequential module composed of linear module with 784 inputs, 30 outputs, a ReLU function that will just automatically take in the 30 and chuck out 30 more. Then we pass that into a linear module that will take in 30 and output 1. Okay, let's just write that real quick. So simple net and then dot sequential and then dot linear 28 by 28 30 and then dot ReLU and then dot linear 31. Okay, so this is just a composition here. So and then sequential creates a module that will call each of the listed layers or functions in turn. And then .ReLU is a PyTorch module that does exactly the same thing as f.ReLU function. Most functions that can appear in a model also have identical forms that are modules. Generally, it's just replacing f with nn and changing the capitalization. When using nn.sequential, PyTorch requires us to use the module version. Since modules are classes, we have to instantiate them, which is why you see nn.ReLU in this example. Okay, because nn sequential is a module, we can get its parameters, which will return a list of all the parameters of the module it contains. Let's try it out. As this is a deeper model, we'll use a lower learning rate and a few more epochs. Wait, first let me print out what SimpleNet looks like. That'll help us visualize. So here is going to be sequential. We have a linear layer or linear module. We can just call it layer 2. With 784 inputs, outputs is 30 with a bias. Then ReLU, and then 30 input features, 1 output features, and with bias. Okay, so let's create the learn instance. Learner. So we'll pass in data loaders. We'll pass in our simple neural net. The optimization function will our optimizer will still be SGD. Loss function will be mnist loss, and then metrics function is going to be batch accuracy. Okay, now we just need to call learn.fit, and we're going to use an epoch that's 10 times smaller. Hopefully converges better. Oh yeah, you get better accuracy. Look at that. And then the training and validation are also in check with each other. Ooh, this thing got smarter. So we're not showing the 40 lines of output here to save room. The training process is recorded in learn.recorder with the table of outputs stored in the values attribute. So we can plot the accuracy over training. So here it is. So let's just use the plot plt dot plot l learn.recorder dot values what is it dot item got, I don't know what that stands for, 2. Okay, so then we can view the final accuracy too. So learn.recorder dot values, last dimension, I guess. Okay, cool. I wonder what this returns really. What is it? I'm guessing this is the training loss, validation loss, and then accuracy. So the last log entry. Okay. So at this point, we have something that's rather magical. A function that can solve any problem to any level of accuracy, the neural network, given the correct set of parameters. A way to find the best set of parameters for any function, stochastic gradient descent. This is why deep learning can do such fantastic things. Believing that this combination of simple techniques can really solve any problem is one of the biggest steps that we find many students have to take. It seems too good to be true. Surely things should be more difficult and complicated than this. Our recommendation, try it out. We just try it out on the MNIST dataset and you've seen the results. And since we are doing everything from scratch ourselves, except for calculating the gradients, you know that there's no there's no special magic hiding behind the scenes. Going deeper, there is no need to stop at just 2 linear layers. We can add as many as we want as long as we add a nonlinearity between each pair of linear layers. So some sort of like ReLU in between as a sandwich. Therefore, you stop the model from just having like collapsing into one linear model. As you will learn, however, the deeper the model gets, the harder it is to optimize the parameters in practice. Later in this book, you will learn about some simple but brilliantly effective techniques for training deeper models. We already know that a single nonlinearity with 2 linear layers is enough to approximate any function. So why would we use deeper models? The reason is performance. With a deeper model, one with more layers, we do not need to use as many parameters. It turns out that we can use smaller matrices with more layers and get better results than we would get with larger matrices and few layers. That's an interesting phenomenon. So if you want to go not deep but shallow, you need to have more parameters in every tensor. But if you go deeper with more layers, each tensor can be smaller with less parameters. That's really interesting. And overall, the number of parameters then would be less. So that means that we can train the model more quickly and it will take up less memory. In the 1990s, researchers were so focused on the universal approximation theorem that few were experimenting with more than one nonlinearity. This theoretical but not practical foundation held back the field for many years. Some researchers, however, did experiment with deep models and eventually were able to show that these models could perform much better in practice. Eventually, theoretical results were developed that showed why this happens. Today, it is extremely unusual to find anybody using a neural network with just one nonlinearity. Here's what happens when we train an 18-layer model using the same approach we saw in Chapter 1. So, ResNet is going to be used here with CNN Learner. So, wow, with just one epoch, it becomes a 99%, 99.7% accuracy. Cool. So nearly 100% accuracy. That's a big difference compared to our simple neural net. But as you'll learn in the remainder of this book, there are just a few little tricks you need to use to get such great results from scratch yourself. You already know the key foundational pieces. Of course, even when you know all the tricks, you'll nearly always want to work with the pre-built classes provided by PyTorch and fastai, because they save you from having to think about all the little details yourself. Jargon recap. Congratulations! You now know how to create and train a deep neural network from scratch. We've gone through quite a few steps to get to this point, but you might be surprised at how simple it really is. Now that we are at this point, it is a good opportunity to define and review some jargon and key concepts. A neural network contains a lot of numbers, but they are only of two types: numbers that are calculated and parameters that these numbers are calculated from. This gives us the two most important pieces of jargon to learn: activations, so numbers that are calculated. So numbers are calculated by both linear and nonlinear layers. So these are just like the results of your linear and nonlinear layers. So in this case, each one of these things here, right, produces a result on our activations. Okay, numbers that parameters are numbers that are randomly initialized and optimized. That is the numbers that define the model. We will often talk in this book about activations and parameters. Remember that they have specific meanings. They are numbers. They are not abstract concepts, but they are actual specific numbers that are in your model. Part of becoming a good deep learning practitioner is getting used to the idea of looking at your activations and parameters and plotting them and testing whether they are behaving correctly. Our activations and parameters are all contained in tensors. These are simply regularly shaped arrays. For example, a matrix. Matrices have rows and columns. We call these the axes or dimensions. The number of dimensions of a tensor is its rank. There are some special tensors. Rank 0 is a scalar, rank 1 is a vector, rank 2 is a matrix. A neural network contains a number of layers. Each layer is either linear or nonlinear. We generally alternate between these two kinds of layers in a neural network. Sometimes people refer to both a linear layer and its subsequent nonlinearity together as a single layer. Yes, that is confusing. Sometimes a nonlinearity is referred to as an activation function. Yeah, that's the reason why I get so confused, because here's the thing. Yeah, so these all produce activations, right? But then we call like only the nonlinear layer activation function. I just don't understand that terminology. If all of these are activations, aren't they all like why is this one called activation function? Is it because it's a function that makes things nonlinear? But if this is a linear thing and we call the product or like whatever the result of this an activation, then it has nothing to do with it being either linear or nonlinear. So I don't know. So sometimes a nonlinearity is referred to as an activation function. So that's confusing to me. Actually, you know what? Let's do this. Okay, so if a result of a linear or non-linear layer in a neural network is called an activation, why do we refer to the nonlinear layers? Let me be consistent. Nonlinear layers as activation functions. This doesn't make sense to me, as a result of a linear layer is also called an activation. So why are nonlinear layers such as ReLU so special to get a name like activation function? Boom. Okay. You're right to notice the naming is a bit sloppy. It's historical and convenience more than perfect logic. Why the output is called an activation. In neural nets, people often call the value inside a neuron or inside a layer its activation, basically what that unit is doing right now. Depending on the textbook, activation might mean pre-activation, basically the linear result, and then the activation, whatever the nonlinear function is. In practice, lots of people casually call either of these activations, especially when logging tensors during training. Get activations from layer 3, even if that layer is linear. So what is this letter? You know what? Let's do a combination of cloud LLM and and local LLM. Let's use GPT OSS. Okay. Yeah, that looks right. Cool. What is this letter? I don't want to say it on camera. I know what it could be, but my math is always so fuzzy. Okay. It's phi. Yes, it's phi or phi. Yeah. Actually, you know what? How do you pronounce phi or phi? Come on. You think too much. There we go. Okay. Okay, well, it's already there. Phi. It's called phi. In modern Greek, it's pronounced phi. Okay? When used as a mathematical symbol, it's usually just called phi. Okay. All right, too much. All right, cool. So why phi got the special label activation function? Historically, going back to perceptrons, early neuroscience-inspired models, the idea was compute an input drive Z, or actually let's make sure let's read our stuff correctly. Okay. Be concise. Be concise. What is this letter? What is this Greek letter? What is this Greek? Zeta? Maybe? I don't know. Yeah, it is. Zeta. 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 Okay. Maybe let's change my right here. Just be concise. Be concise. You are a helpful and knowledgeable assistant about science, technology, what else? Engineering and math. Be concise in your answers. Okay? Great. We'll save this preset as STEM assistants. Cool. Okay. Okay. Good enough. All right. So, sorry, just a bunch of tangents. Okay. So now where were we? Okay. Why phi got the special label? Okay. Apply a squashing threshold-like rule that decides whether the neuron fires. So that squashing and threshold rule is what activates the neuron in the biological metaphor. So the nonlinearity phi became the activation function. So even when modern nets like ReLU, not very biological, the term stuck. Okay. The deeper reason without nonlinearity, the whole network collapses. This is about the whole linearity thing. Okay. Just trust me on that. Okay. Yeah, so basically it's just being lazy and not really caring about your terms. Okay. Cool. Let's learn our vocabulary. ReLU, the function that returns 0 for negative numbers that doesn't change positive numbers. Mini batch is a small group of inputs and labels gathered together into arrays. A gradient descent step is updated on this batch rather than a whole epoch. Forward pass is applying the model to some input and computing the predictions. Loss is a value that represents how well or badly the model is doing. Gradient is a derivative of the loss with respect to some parameter of the model. Backward pass is computing the gradients of the loss with respect to all model parameters. Gradient descent is taking a step in the direction opposite to the gradients to make the model parameters a little better. And then loading rate is the size of the step we take when applying stochastic gradient descent to update the parameters of the model. Okay, so choose your own adventures reminder. Did you choose to skip over chapters 2 and 3 in your excitement to peek underneath the hood? Well, here's a reminder to head back to chapter 2 now because you'll be needing to know that stuff soon. Okay, we're reading cover to cover, so it's fine. I'm gonna skip questionnaire. I'm gonna skip questionnaire. Okay, let's do some practical stuff. Actually, wait. No. Let's continue to image classification after this. Okay. Yeah, let's continue. So, This one was what, chapter 4? Let's just check that in. And then we'll continue with chapter 5 next time. Oops. Wait, what? Oh, there we go. Okay. I think that's it. Next time.